is indeed twice the yellow vector, gradient g. Okay, that's where you read the value of lambda. Okay. And we have the other solution, which is somewhere here, negative root 3, and there, again, lambda equals 2. The two vectors are proportional by a factor of 2. Yes?
So solutions are guaranteed.
No, solutions are not quite guaranteed to be absolute minima or maxima. They're guaranteed to be somehow critical points under the constraint. So that means, if you were able to solve and eliminate a variable, they would be critical points. So then you have the same problem as with critical points. Are they maxima or minima? And the answer is, well, we won't know until we check. Okay. More questions? No? Yes? So what is a Lagrange multiplier? Well, it's this number lambda is called the multiplier here. Okay? It's a multiplier because it's what you have to multiply gradient of g by to get gradient of f. It multiplies. Okay. So let's try to see why is this method valid. Because, so far, I've shown you pictures, and I've said, well, see, they're tangent. But why is it that they have to be tangent in general? Okay, so let's think about it. Let's say that we are at a constraint min or max. So what that means is that if I move on the level g equals constant, then the value of f should only increase or only decrease. But it means in particular to first order, it will not change. Okay? That's this, so at an unconstrained min or max, the partial derivatives are 0. In this case, the derivatives are 0 only in the allowed directions, and the allowed directions are those that stay on the level surface, g equals constant. Okay? So in any direction along the level set g equals c, the rate of change of f must be 0. Okay, that's what happens at minima or maxima. Except here, of course, we look only at the allowed directions. Okay, so let's say the same thing in terms of directional derivatives. So that means for any direction that's tangent to the constraint level g equals c, we must have df ds in the direction of u equals 0. Okay? Let me maybe draw a picture. So let's say now I'm in three variables, just to give you different examples. So here I have a level surface g equals c. I'm at my point, and if I move in any direction that's on the level surface, so I move in a direction u that's tangent to the level surface, then the rate of change of f in that direction should be 0. Okay. Now, remember what's the formula for this guy? Well, we've seen that this guy is actually gradient f dot u. So that means any such vector u must be perpendicular to the gradient of f. Well, so that means that the gradient of f should be perpendicular to anything that's tangent to this level. So that means the gradient of f should be perpendicular to the level set. That's what we've shown. But we know another vector that's also perpendicular to the level set of G, that's the gradient of G. So we conclude that the gradient of f must be parallel to the gradient of G, because both are perpendicular to the level set of G. Okay? I see confused faces. So let me try to tell you again where that comes from. So we said if we have a constrained minimum or maximum, if we move in the level set of G, f doesn't change. Well, it doesn't change to first order. Remember, it's the same idea as when you're looking for a minimum, you set the derivative equal to 0. Okay, so the derivative in any direction tangent to G equals C should be the directional derivative of f in any such direction should be 0. That's what we mean by a critical point of f. And so that means that any vector u hat, any unit vector tangent to the level set of G is going to be perpendicular to the gradient of f. So that means that the gradient of f is perpendicular to the level set of G. If you want, that means the level sets of f and G are tangent to each other. Okay, so that's justifying what we've observed on the picture, that the two level sets have to be tangent to each other at the constrained minimum or maximum. Okay, does that make a little bit of sense? Kind of. I see at least a few faces nodding, so I'll take that to be a positive answer. Okay, so since I've been asked by several of you, how do I know if it's a maximum or a minimum? Well, warning, the method doesn't tell whether a solution